Hello everyone, I'm Prashant Rajput, a third year PhD candidate at NYU, and I'll be presenting my work on non-intrusive malware detection for ICS, done under the guidance of my advisor, Professor Mikhail Takos. Due to increased operational performance, profit margins, and improved monitoring, IoT devices are continuously integrated into the operational technology sector, a move dubbed Industry 4.0. As companies integrate IoT with OT, managing security and privacy is of topmost priority. However, traditional machine learning based malware detection techniques cannot be directly applied to these OT devices due to certain constraints such as limited computational capabilities, strict adherence to real-time requirements for regulating critical physical processes, dependence on legacy or proprietary operating system which limits access. Consider Vago PFC100 controller, a device equipped with ARM Cortex-A8 operating at 600 MHz with a main memory of 256 MB. Such a device cannot directly employ state-of-the-art machine learning-based solutions and other approaches such as virtualization, sandboxing, and more. Therefore, there is a need for another approach to this problem. To tackle the constraints put forth by OT devices, we consider the use of JTAG, an IEEE 1149.1 standard for testing and verifying PCBs that can also perform system-level debugging. JTAG's debug access port connects directly to the buses capable of accessing memory and provides non-intrusive data access from the main memory. Furthermore, by utilizing out-of-the-device virtual to physical address translation and computation, intensive operations can be shifted outside of the OT devices for performing machine learning-based static analysis malware detection, a tool we call Amaya. Amaya extracts instruction sequences by moving a 32-byte window incremented by 1 byte over the Hilbert curve and calculating a 256 x 256 matrix of entropy values covering a 2 MB file size. The utilization of the Hilbert curve preserves locality after the flattening of the entropy matrix. Furthermore, as shown in Figure 1, more than 97% of the samples we utilize for experiments are less than 2 MB, and the step size is adjusted accordingly to fit in 256 x 256 matrix. We also extract ASCII strings considered to be at least of length 6, hashed between 0 to 16, and paired with log base 1.25 to create a 16 x 16 histogram. Similarly, we also create a histogram for all the system calls in the binary. Intuition for the selected features is to model the ELF binaries in a platform-agnostic manner. We do not preserve its functionality in these features, but instead the ELF binary content and similarities between different variants using strings and system calls. We then perform standard scaling and downsample the features to study the variation in malware detection accuracy by employing SVM for classification. Due to the utilization of platform-agnostic features, Amaya can be easily generalized, so we test it on both ARM and x86-64. For our experiments, we utilize more than 9,200 samples for ARM and upward of 6,000 samples for x86-64. As shown in Figure 2, pre-processing makes differentiating malware from goodware easier. The SVM model for ARM provides an accuracy of 98% for a downsampling rate of 64, meaning the final length of the feature vector is 64. On the other hand, the SVM model for x86-64 provides approximately 95% accuracy for a DSR of 81. We also study concept drift, a phenomenon due to which the machine learning model's accuracy starts to decrease with the introduction of new data changing over time. This requires model retraining, and as evident, the accuracy decreases due to the introduction of new variants and new malware. Finally, we also study spatial experimental bias and observe that machine learning models' performance remains high. Before concluding, let us quickly look at some of Amaya's assumptions and limitations. Non-intrusive memory access requires an accessible JTAG port on the target device. There is also a need for limited knowledge of the operating system to locate the process text section and perform out-of-the-device address translation. Furthermore, JTAG is slow in extracting data. Linux also employs selective mapping of process address space, which might lead to partial binary retrieval. Finally, a privileged adversary can override the memory-mapped operating system lock access register to restrict external debug access. Such a situation can be prevented by using a hardware watchpoint to monitor these addresses. In conclusion, we propose Amaya, an out-of-the-device, non-intrusive, machine learning-based static analysis malware detection tool for the OT sector. Thank you.